and welcome to a new module. So this one will be on I/O. To go through I/O, we will be covering first the hardware elements of where do you store information, and specifically for purposes of I/O, what I will be going through is more of the block storage media, the random I/O, then other I/O mechanisms that exist. So first of all, I'll cover storage media. There are two types, hard disk drives and solid state drives. Then how does the storage media interconnect to a system, to the server system, and the protocols, SAS, CASI, and lately NVMe. Then I get back to the operating system parts of how does a Linux file system connect to this storage media, how does Linux files work, and then basically, because it is block I/O that we are dealing with, looking at block I/O performance, as well as how can you control this block I/O for a particular process. So without further ado, let us get through the first lecture here today, which is on hard disk drive storage media. A hard disk is essentially a disk that stores information on platters, and the platters are circular metal plates that are coated with a magnetic material. These magnetic material can be magnetized, which essentially help storing information on that magnetic material, which you can retrieve back again when you want to read it back. The platter diameters that are available and are typical now are either the 2.5 inch ones or the 3.5 inch ones. Hard disk drives are accordingly built and available as 2.5 inch drives or 3.5 inch drives. The platter itself has magnetized areas that are written in concentric rings on the platter. These are called the tracks. So tracks are circular rings, and you can have several hundred thousands of circular rings on a platter. Imagine these are like the rings on a tree when you cut through a tree trunk and you see all the rings. It's exactly like that. Each platter can be magnetized on both sides. So you can have two magnetized sides per platter, and that adds to the capacity on each platter. Now lately, so right now you can store like 1 terabyte per 2.5 inch platter and up to 2 terabytes per 3.5 inch platter, and that'll mean about half a terabyte on each side of the platter in a 2.5 inch disk. The capacity is the most important element of these disks, and the capacity density itself can be measured in terabits per inch, and by 2015 we had crossed 1 terabyte per inch, which led to getting the 1 terabyte drives, one per 2.5 inch platter. Now these platters have information at various parts, and an actuator arm will actually read this information. But the way it works is there is actually a rotation that needs to happen on these platters. So in the center, there is a spindle motor in the middle of the platters that turn these platters. These motors can turn at different speeds. The predominant speeds available are 5,400 RPM, 7,200 RPM, 10,000, and 15,000 RPM. RPM is a standardized unit that you will often be able to see on hard disks, and it is measured in rotations per minute. So the faster the disk is rotating, the faster the head can reach where the storage information is and get access to that information faster. So the way it works is there is an actuator arm that has a read and write head transducer at the end. So the arms are moving the head across the disk on its outside tracks or its inside tracks, and the heads get on the track to read. And this read and write arm is known as the actuator. When the head gets on top of the track, it just has to wait for the spinning to complete such that the data that it wants to read is available. Now within a track, the data is divided into sectors. So a track will be logically divided into many sectors on each track, and the information is stored in the sector. So the the disk is going to read back information from a sector. So the sector becomes the smallest unit that you can ask for from a hard disk. So a platter has many tracks on it. A platter has 2 sides to it, and each track is divided into sectors. To increase capacity further, when you actually build hard disks, of course, you can have a single platter hard disk, but ultimately there's a capacity constraint. So there are more than one platters available on the higher storage hard disks. Each has its own head, each has its own actuator arm, but the arm can only go to one track across all of these, and all the tracks at the same distance on all these platters, all equivalent tracks are envisioned as a cylinder. So that's why they're called a cylinder. There's more than one platter. The same track across each platter forms a cylinder shape, so they're called cylinders. All heads move simultaneously from one cylinder to another. It's not like you can have on one platter a head on track 0 and another one on track 100. They're always going to be on the same cylinder. The older way to measure was more physical addressing, and there was a cylinder head sector addressing. So you know the cylinder, and then you need to know the head, which means which side of the platter, and where exactly on that track, which is the sector. So CHS addressing was available. This was more on the older drives, and now it's more on the logical block addressing. So a drive exposes itself outside as sectors, sector 0 to n, n is the maximum number of sectors. And the specification of a disk capacity is based on the sector size, which is typically 512 bytes and times the number of sectors. This way, the disk is able to not expose the inner physical distribution of the sectors and only makes available the total number of sectors available. And by the sector number, it has the interface back to the system that wants to read information. The platters are put together into a hard disk drive. So the hard disk drive is more than just the storage, which is in the platter. The hard disk drive contains the platters, which of course are 2.5 or 3.5 inches, depending on the drive you are in. Each, you can have more than one platter, and typically this goes 1 to 5, not more than that. And the number of read heads, a platter has 2 sides, so you get 2 read heads per platter typically. Then the platter, of course, there's a motor in the hard disk drive that's going to move the platter that we just talked about. A hard disk drive also exposes itself externally, so you can actually read information and write information to the drive. That happens through standard interfaces, and the standard interfaces available on hard disk drives that have been standardized are SATA, which goes up to 6 gigabits per second, and with SAS 3 standard, you can go up to 12 gigabits per second. So that's the external interface to read and write information. A hard disk also has a buffer cache memory, so as it reads information, you can do various things like read ahead of information and manage an operation command queue. And so there's a small cache here. It's not usually large, but there is an SRAM or DRAM cache available. The controller here is finally where the logic sits. It's a microcontroller. It manages the interaction of the SAS-SATA interface coded into it. It manages the buffer cache. It manages the asks from the actuator to read the data. So that's how this whole thing works put together. Now, from a usage standpoint, there is also the throughput and the access times that are important. And hard disks typically have sequential read-write throughputs, 100 ranging up to 300 megabytes per second. Now, it is important to understand sequential here, because once the head is on a track, then as the track is moving, the head can keep on reading without changing itself again to another position. So that is the fastest mechanism that a head is able to read information from the disk. And that is why the sequential speed is pretty fast, which means the head is positioned, you don't need to move again, and now you just read, and the maximum throughput you can read then is the sequential read-write throughput. When the head has to move to a different location, there is a seek time to get to the other location, and that is directly proportional to the speed that the disk is spinning with. So a 15,000 RPM disk will get you 2 milliseconds for half a rotation. And we take half a rotation into account because on an average, you'll be half a rotation away. Sometimes more, sometimes less, depending on the position you're at from the target position that you want to be at. So the average seek time is calculated at, what does the disk take to complete half a rotation. On 7.2K RPMs, this is at a little over 4 milliseconds per half a rotation, and for 5,000 RPM drives, it is about 6 milliseconds for half a rotation. So let's assume a 4 millisecond seek time, and we are working with a 7.2K RPM drive. You can mathematically derive that you cannot get more than 250 operations per second if each seek time was 4 milliseconds. And that will roughly limit you down to just about 1 megabyte per second if you assume that each read is a 4 kilobyte block size read that you wanted to do, which is about 8 sectors that you read for each operation. So a random read is low, the speed, but sequential reads can give you high throughput. This is also why when you use hard drives, you want to defragment them such that more information is available next to each other to get you that sequential read. And especially when you're working with laptops, defragmentation is something that you want to do often. Let us look at a hard drive specification. I took a Seagate drive, that's a 2 terabyte drive. And you can read these specifications and make sense out of what I just talked through. So it has a form factor of 2.5 inches, and it has 2 platters, and each platter has 2 heads, so a total of 4 heads that can read information. The capacity of the drive is 2 terabytes, so 1 terabyte per platter. It manages a cache of 256 megabytes, and then that's the total amount of information it can store in its buffer cache. Supports SATA 6 gigabits per second interface to it. Another interesting parameter is the endurance parameter here specified by the drive, and it says 2 million hours mean time between failure. So if you keep the drive running, and you can get 2 million hours on it before it will fail. Ultimately, it is a mechanical device. It is going to fail. Drive providers have a certain threshold for when is it expected to fail, and so this one it has an endurance value of 2 million hours. There is power consumption for these drives as well: 8 watts active, 5 watts idle power consumption. So the RPM on this drive is 7,200 RPM. This is a 7.2K drive. Giving you a sequential read throughput of up to 225 megabytes per second, as well as a sequential write throughput of 225 megabytes a second. Now, the random reads are not specified on these drives, but you can just roughly calculate it to, based on the previous formula, and so it won't be very high, but random read tests use 4 kilobyte IOPS operations, and you can have a queue depth of 32, which means you have 32 commands in parallel available in the queue. There are other tests with the queue depth of 1 as well done on these, but on the hard drive, roughly the ability to do random read and write will be limited by the seek time, essentially. So that was it on the hard disk drives. The next lecture in I/O will be on storage media solid state drives, which is where a lot of the modern disks are being developed in solid state now. Thank you. Bye.